Next, we will discuss how to do calculus with the hyperbolic arc cotangent function. Let's consider the hyperbolic arc cotangent function and let's find its derivative. Of course, we can use the limit definition of the derivative, however, we get stuck quick. But let's not forget the alternative definition of the hyperbolic cotangent function. We can differentiate this function using the chain rule, which is particularly easy when applied to the natural logarithmic function. Simplifying the expression produces a surprisingly nice result. In summary, we now have the formula for the derivative of the hyperbolic arc cotangent function, as well as the formula for the antiderivative of its derivative. You might have noticed that the hyperbolic arctangent and the hyperbolic arc cotangent have exactly the same derivative. The key difference is in the domain of each function. The hyperbolic arc tangent only exists between -1 and 1, and the hyperbolic arc cotangent only exists when the input is greater than 1 or less than -1. Let's, for example, find the derivative of the following function. We start the process by recognizing that we have to find the derivative of a composition of the hyperbolic arc cotangent function applied to the square function, which is equal to the following expression, in which we know how to find all the components. We get the final answer after plugging everything in and simplifying. Let's, for example, find the derivative of the following function. We start the process by recognizing that we have to find the derivative of a composition of the square root function applied to the hyperbolic arc cotangent function, which is equal to the following expression, in which we know how to find all the components. There isn't much to simplify after we plug everything in. Let's do an example of an integral. We first recognize the pattern and rearrange the integrand. Then we set up the substitution by setting a new variable, let's say t, equal to the hyperbolic arc cotangent, and finding the differential of t. Next, we plug everything into the original integral, and notice how, because of the discovered pattern, we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function back for t. Let's do an example, this time of a linear substitution. We set up the linear substitution by setting t equal to 6x and finding the differential of t and expressing the x in terms of dt. As a result, we have a simple indefinite integral in terms of t. Because of the domain, we choose the antiderivative to be the arc cotangent function. Now we replace the original function back for t to get the final answer. We discussed how to differentiate and integrate the functions that have the hyperbolic arc cotangent as one of their components.